Okay. Hi everyone. So first of all, I would like to thank the organizers for giving me the opportunity to say something about my works, which basically deals with the radiations of the ultralight particles that Monibroto and Alexei told about. Okay, but from the compact stars, and I will tell what is the effects of the neutrinos if you have the radiations of such kind of particles. So I will also tell that neutrinos can also be radiated from the binary systems, and standard model allows that one of the neutrino mass eigenstate can have a very small mass. Okay, so in that scenario you can have a very small mass neutrino emissions from the binary. Okay, so as we all know that the direct detections of the gravitational wave was discovered in 2015 from the binary black hole merger, but indirectly it was first studied by Hulse and Taylor by observing a binary system which is called the Hulse-Taylor binary system. So it consists of one neutron star and one pulsar. So basically from the Earth you see the lights which is coming from the pulsars at a periodic rate, okay, and from there you can actually plot what is the orbital period of the binary. So you will see that over an expansion of like 30 years, so you will see that the orbital period decays with the time, okay. So the reason of this is basically the gravitational wave is radiating from the binary system, and it effectively reduces the energy of the system and the orbital period decreases, okay. So that is the first indirect evidence for the gravitational wave from the pulsars, PSRB 1913 plus 16, the Hulse-Taylor binary. And for that, Hulse and Taylor get the Nobel Prize in 1993. Okay. Now, one interesting thing is that if you, so this binary is kind of a very stable orbit, which are very far away from each other. Okay. And if you measure the orbital period, which is roughly of the order of 8 hours, so if you convert it to the frequency range, okay, you will see it's roughly of the order of 10 to the power minus 19 eV. So this is in the ballpark of the fuzzy dark matter. So if we assume that there is some dark matter which has some coupling of the particles in the binary system, then it can radiate such kind of ultralight particles. Okay. So brief motivation for the dark matter. So dark matter has been verified in several scales, like from the galactic scale of the galactic rotation curve, the cluster scale where you can see the bullet cluster observations from the Chandra observatory, and also in the megaparsec scale from the CMB fluctuations you can put bounds on the dark matter. So you need dark matter to explain these fluctuations on the CMB. Okay, so if you consider that the dark matter is basically has a particle nature, so particle is something which is the fluctuations of the field. So it can have mass like from the horizon scales 10 to the power minus 33 eV to the Planck scale, but you can basically reduce the mass scale. As you can see, the mass scale can be of the order of 10 to the power minus 21 to 22 eV. So that is obtained from the phase space calculations. Okay, so basically you see the smallest scale galaxy, which is the dwarf galaxy, and you can assume that this dark matter, if it is in the halo of this dwarf galaxy, then it gives 10 to the minus 22 eV dark matter, which is very much light, the ultralight. Or you can have a very high TeV scale mass dark matter, and then you can search at the colliders. So beyond MP, beyond the Planck mass, you can also have the dark matter which are not the particle dark matter. So these are basically the astrophysical objects like the primordial black hole. So those can also be the dark matter. So one of the motivations of studying this fuzzy dark matter or like light dark matter is basically one is the Korkas problem, which is the small scale structure issue in the universe or the galaxies, and this is the direct detection experiments. So you can see, so if you plot the density with the scale of the galaxy, you will see that this behavior is basically if you assume that your galaxy contains the standard pole dark matter, the NFW, okay. But the observation predicts that you have some pole-like structure at the 1/3 kiloparsec of the galaxy. So this is called the Korkas problem. So this cannot be explained from the standard WIM particle. So you need fuzzy dark matter. So fuzzy dark matter is basically whose mass is very light. Okay, so your de Broglie wavelength is of the order of the size of the dwarf galaxy. So the basic principle is from the Heisenberg uncertainty principle. So as Heisenberg uncertainty principle tells you that you cannot localize the electron in an atom. So basically, if your wavelength of the dark matter, since the mass is very light, your wavelength is very large, so you cannot localize the dark matter inside at the core of the galaxy. So you have a coal-like structure from the fuzzy dark matter, okay? And at the large scale, it satisfies everything. Also, from the direct detection experiments, the regions are mostly ruled out from those experiments. So this is one of the also motivations to study the other alternative scenarios than the WIM dark matter. So this is the typical expressions of the wavelength of the dark matter, fuzzy dark matter rather. So it's of the order of 1.92 kiloparsec, the typical size of the dwarf galaxy, if your mass is of the order of 10 to the minus 22 eV, okay? So for this kind of very light mass, and if your local dark matter density is 0.4 GeV per centimeter cube, you can calculate that the number density within the de Broglie wavelength is very large, okay? So since the number density is very large, all the fields can behave coherently, and you can treat the field as a classical wave, okay? So if you have some classical dark matter field, you can typically write the potential as like this, where you can see there are two scales like mu and Fa, which has some shift symmetry, okay? And the two scales, and basically if you take the double derivative of the potential, you will get the mass. So you will get the two scales as mu and Fa. So typically for the QCD actions, the mu, if I am assuming the dark matter is a QCD, this mu is basically the lambda QCD. So where at some U1 symmetry breaks explicitly at that scale, and Fa is the symmetry breaking scale where U1 basically breaks, and at that point basically the mass of the scalar field is 0, okay? So it gets mass at the QCD scale, that is the mu. But for axion-like particles, which is not exactly the QCD actions, this mu can be anything. So yeah. So typically that is told by Monibroto that you can, for that potential, you can write the equation of motion for the scalar field as this for different momentum modes, okay? And for the zero modes, you can actually have the solutions that is depicted in this. So if you consider that your Hubble is basically much greater than the mass, so the field is basically constant, so you can have a straight line there. And this field starts oscillating when basically the h is of the order of ma, okay? So if you compare h, the t square over m Planck, with the mass of 10 to the minus 22 eV, so your temperature is 500 eV. So at that temperature, the oscillation dominates, okay? And you will see that you can calculate the late time energy density of that scalar particle. So that is m square a square, okay? And at late times when the oscillation starts, you will see the behavior of A is like this, t to the power 3 by 2. So when you take this, so rho goes as t cube. So t is basically proportional to 1 over A, so it redshifts like a cold dark matter. So in that way you can solve the relic density. So this is the relic density expressions for the fuzzy dark matter, okay? So you need a very high scale to produce that dark matter, which is of the order of say Gauss scale, and you have a very small mass to get a typical relic density as 0.12. So this is the brief motivation, the core cusp problem and the direct detections. Now as we know that the neutron stars, so what we are looking is basically this type of particles can emit from the binary systems. So as neutron stars contains the nucleons, hyperons as well, also it contains some muons. So if my electron chemical potential is very large, and if my electron Fermi energy is much larger than the muon, then the muon decay is Pauli blocked, and one can have some substantial amount of muons within the neutron stars. So that was calculated by Garani and Julian Hick, and they have calculated what for certain equations of state you can get the number of muon as order of 10 to the power 55 compared to the typical nucleon numbers, which is 10 to the power 57, okay? So if you have this kind of muons in the neutron stars, okay, then you can actually consider some symmetries, which is in an anomaly free way. You can construct this symmetry in the standard model and you can gauge it. So you can model that my gauge bosons of certain L mu minus L tau type can have some coupling with the muons in the neutron stars. So that type of L mu minus L tau type of gauge bosons can emit from the binary systems. So So this is the typical coupling that one can consider, which is G is the typical coupling, and Z mu prime is the L mu minus L tau gauge boson, and J mu is the current in the neutron stars. So this is a kind of a one vertex process, and you have to calculate what is the emission rate for the Z mu prime. So we calculate this d gamma. So basically take the amplitude square and the energy momentum conservation in the phase space, and you have to take also the polarization sum for the gauge bosons. So we did these things and we get dE dt of this. So now you have to fix J mu. So J mu looks like this, of the order of Q u mu, the J mu is basically rho into V. So basically the charge is the typical muon charge, okay? And you can construct a Keplerian orbit and you can parameterize the orbit in this way. And the fundamental frequency of the binary system is like this, okay? Gm1 plus m2 over a cube, so this way, okay? Now, one thing is that since the orbit is elliptical, it's not circular, so you have to take the Fourier sum of all the modes, okay? You can't consider only one circular mode. So you can go to the Fourier space and you can get the coordinates in the Fourier space and also the velocities. So this is basically the velocities in the Fourier space, and n is the number of harmonics. So for these things, you can calculate what will be the components of the current, of the muonic current in the neutron stars, and you will get this type of formulas, okay? So the final formula is like this, dE dt of this. So you see that this is the rate of energy loss for, if you consider the L mu minus L tau vector bosons is radiating, okay, where A is the semi-major axis and M is basically the total mass of the system. So it requires a asymmetry in the charge to mass ratio of the binary system for the radiations of the binary for the radiations of the vector gauge bosons, okay. And from this factor, the phase space factor, you can actually get that your N0 is basically the ratio of the mass of the gauge boson and the orbital frequency. So from this, you can say that one needs omega should be greater than mz prime for the radiation to occur. So for Hull stellar binary system, this omega is roughly of the order of 10 to the minus 19 eV. So your mass of the gauge bosons, if it is less than 10 to the minus 19 eV, then these gauge bosons can emit from the binary system, okay. So basically you need to now compare this with the typical energy loss for the gravitational wave, which is standard, and then basically comparing with the data, you can get a bounce on the G, so which is very light, as Alexis was also telling. So you have that for mass of the order of 10 to the minus 19 eV less, you can have the radiations of the gauge bosons, and which coupling is very small, okay. So yeah, so this can be the candidate for the fuzzy dark matter. So the similar principle can also be used for the radiations of the scalar or the tensor particles. So where you have to just change the Lagrangian and follow the same procedure. So this is for the scalar if phi is coupled with the total number density, and for the massive tensor is basically h mu nu t mu nu, and you have to follow the same things. Now following this, these people calculate what is the radiation rate if the neutrinos are emitting, okay. So this is the typical Lagrangian if I am considering that the neutrinos are coupled with the standard model gauge boson, okay, and psi is the current, muonic current. So you will get this P nu as this 10 to the minus 56 eV square. So this is the formula for the standard model of neutrino emissions. So this is much larger than smaller than the usual gravitational wave radiation energy. So the takeaway message is the neutrinos will not give enough energy for or enough energy loss contributions to the binary systems orbital period loss. But you can go to the BSM models where your Z is basically now Z prime, and then you will get the similar type of bounds. So that is they obtained, which is roughly of the order of 10 to the minus 18, okay. So, okay, so that is the one thing. Another thing is we are considering also we have some neutron stars, okay, and as neutron stars is there, so you have some free charges on the neutron stars, and you need to keep the force free equilibrium conditions. That means the total Lorentz force should be 0, and if you want to compensate that Lorentz force, you want a very strong electric field, okay, and if you take the volume charge density for that, you will get the Goldrich-Julian charge density, that is the volume charge density. So that is of the order of omega times b, okay. So you can, so this is the very general or very simplistic scenario where I am considering omega and b are parallel. So you can write the Lagrangian for some scalar field, where the scalar field is coupled with now the Goldrin-Julian charge density. So it's phi rho gj. And you can calculate what is the equation of motion for the scalar field. So that is basically, you will get these solutions. So this was initially done by Spinov and Zhu, okay, that they considered not with the Goldrin-Julian, but some constant charge density, okay. But here my constant charge density, I am assuming that it is omega times b. So you will get a typical behavior of the scalar field as this. So it is different from what Smirnov and Monibrother told, that this phi, this light scalar, has a spatial behavior instead of the temporal behavior, okay. So you can have a scalar field behavior inside the compact state and outside of the compact state. And you can get that it should have a long range behavior if you go very large distance, okay. As you go to the large distance, the phi should fall as 1 over r. So yeah, so for the small scalar mass limit, you will get a 1 over r type of Coulombic like behavior, okay. And you can also consider, if you consider that the wavelength of the scalar field is very large compared to the size of the object, so you can consider that the scalar wave will see the compact object as a point, okay. So you can also do the point source approximations, and you will get a typical Yukawa behavior for the scalar field, okay. So do the same thing. So I am now considering that my field is, instead of the L mu L tau vector, you have a scalar field radiations from the neutron stars, which is the source is where the Goldrin-Julian or the net electron charge. So there can be two charge, either the Goldrin-Julian charge or the net electron charge. So you do the same things, and you will get a similar type of energy loss. So this is for if you consider that the scalar field is coupled with the net electron charge, then you will get a behavior of like this. Or if you consider it is coupled with the Goldrin-Julian charge density, then you will get the energy loss of this form. So the point is that now you have to compare with the typical energy loss for the gravitational wave, okay. So we get a bound on G as like 10 to the power minus 21, which is 2-3 orders of weaker than the usual fifth force experiments. You can also do that. This is the plot for, you have a binary system and then it is emitting. You can also consider that you have a pulsar, which is maybe a Crab pulsar, you can see. So this is the pulsar inside in the Crab nebula, and there can also be radiations of these ultralight particles from the pulsars. And if the radiation is possible, then you can measure observationally the pulsar spin down. So what you can basically want to probe of this type of new physics, you basically compare what is the new contribution, and you compare with the observations of the pulsar spin down. So pulsar spin down luminosity, it is observable, it is measurable. So you do the same thing, you can express phi as a Fourier sum of this phi n r, and you can also have the density of rho n r of this, and you do the equation of motion, so you can get this behavior. So you can do, you can follow the Green's function method, and you can calculate what is phi n r. Okay, so this is the typical Green's function method, and you will get that phi RT goes as like this, okay, and P is basically the dipole moment, okay, which looks like this, is basically Q times R. So this is the formula for the energy loss for if you have a dipole radiations of the scalar field, okay. And I am considering now that the Crab pulsars has a typical magnetic field form. So there are many models, is the dipole rotator models or the aligned rotator model. So one of the model, this B0, the magnetic field has a time variations, and you can get rho RT as this, where theta m is basically called the magnetic pole attitude, which is related with the polar angle, and also with the angle between the magnetic axis and the rotation axis. Okay, so you need a small angle to get the radiations from the pulsar. So following the same thing, you can calculate the energy loss for the pulsar spin down. So that we calculated as this for the, say, Goldrin-Julian, and also for the net electron charge. So here we will getting the bounds which is roughly comparative with the fifth force bound, is 10 to the minus 25. And also from the, you can see these conditions that you need the mass of the scalar should be less than the frequency, orbital frequency of the pulsar, or the rotation frequency of the pulsar. So this will give you 10 to the minus 14. Okay, so you have, if your mass of the scalar is less than 10 to the minus 14 eV, then this kind of scalar can emit from the Crab pulsars or any pulsars, and you will get this kind of bound. So it is comparative with the fifth force bound. So yeah, so we are comparing with the observed value, the spin down luminosity for the pulsar, and we are considering that this scalar can contribute 1% of this. So this is the way you can get the bounds on G. So now the point is that we know that there is a cosmic neutrino background, as Monibrotho told. So cosmic neutrino background's energy is very small, 10 to the -4 to -6 eV, and it is very hard to detect. Okay, but one thing is that if we can detect the cosmic neutrino background, we can probe the universe much earlier than the CMB epoch, because it decouples much earlier than the photon. Okay, so at present epoch, the T nu is of the order of 10 to the -4 eV, and if you calculate what is the number density of these neutrinos, you will see for the Dirac neutrinos, if you include all the particles and antiparticles, you will get n nu is of the order of 336 per centimeter cube. Okay, and also the oscillation data provides that this neutrino the two of the neutron mass eigenstate are non-relativistic today. There are experiments, as he told, that P. Ptolemy can trying to probe this type of relic neutrinos. There is also indirect detections for this type of neutrinos. If you consider that in the background there is relic neutrinos, then it can also affect the CMB fluctuations. So from indirectly also you can make a probe on the relic neutrinos. So one thing is that now I am considering that my scalar is emitting from the pulsar of the neutron stars, and if in the background there is a relic neutrinos, it can get a thermal mass, the scalar field, okay, from this diagram, okay, and then you see that m phi square is basically increases by this amount, okay, for non-relativistic neutrinos, where nu is basically y nu is basically the coupling of phi and nu, okay, and so if the mass is increasing, so basically the length scale is increased. So basically you will detect, or you can probe mass larger than whatever mass you obtain for when there is no neutrinos, because the mass is increased. Okay, so the length scale decreases. So that is the scalar mass corrections that you can see. Okay, and if you consider that I have a CNUB background in my radiations of the scalar particle from the neutron stars or the pulsars, the bounds will be changed. So if you consider y nu equal to 0, this is the strongest bound that I told you. Now if you consider the y nu is roughly of the 10 to the 8 or 10 to the 9, so these bounds will not be as stringent as this thing. So the bounds will become weaker in presence of the CNUB background. So yeah, so this is the thing. Also one thing that I just want to say that we know that the neutrinos are emitting from a core collapse supernova or from merging neutron stars, okay, and when the neutrinos are coming, it makes the stellar object cool. But some of the neutrinos, when it is coming through the stellar material, it can basically annihilate to produce electron and positron, and this electron and positron annihilate to give you the gamma ray photons, and this can be one of the way to energize the gamma ray burst. So the typical energy for the gamma ray burst is of the order of 10 to the power 52 arc. So if you calculate this process and you calculate what is the energy deposition for this nu bar goes to E plus E minus, you will get for different backgrounds, as you are considering compact stars, the geometrical effects or the background effect is important. So if you consider in the Newtonian background, you will get 10 to the power 50 arc, 2 orders of magnitude smaller what is from the maximum, say. And if you consider Schwarzschild, you will get a 1 order better than the Newtonian result. So we calculate, we consider that if this process is existing, nu bar goes to E plus E minus, which will give you the typical GRB energy, and then we are considering that we are extending our standard model with some U1 B minus L. So you can also have a Z prime mediated process from nu bar goes to E plus E minus, and we calculate what is the energy depositions for the electron and the muon and tau neutrinos. Okay, so in the G prime goes to 0 limit, you will get this formula, which was calculated by Goodman, Dar, and Nusinov in very early time, 1987. Okay, and there is also some factor theta nu r, which depends on the background geometry. And then we actually consider different background, and we obtain a probe on G prime B minus L, and this is a typical type of bounds that you can get from the GRB observations. Yeah, so thank you from this. So I can
time for questions, comments. Sure, Gunther.
Connected to super radiance?
A super radiance?
Yes, because you lose energy at the mass of the scalar particle that's comparable to the rotation frequency.
Yes, actually we didn't calculate the super radiance. Super radiance is mostly effective when you have a black hole. So our system is the neutron star. So yes, of course, the super radiance is basically when your horizons, basically the Schwarzschild radius 2 gm is of the order of the mass scale of the scalar which is emitting. So roughly 10 to the minus 11 to 10 to the minus 12 dB if you convert the Schwarzschild radius to the mass scale. So you can actually calculate also the super radiance, and you can get bounds on those kind of scalar particles from the super radiance of non-observations of super radiance from the black hole. But this is a neutron star. This is a whole different game.
You also have super radiance around neutron stars.
You can also get super radiance around neutron
so
stars.
Do you get different bounds from considering
yes,
super
so
radiance? It's not related to what you do, right?
So basically if you see, okay. Initially when I was talking that you have say light particles emitting, L mu minus L tau emitting from the binary neutron star system, the mass scale is basically determined from the orbital frequency. So I told you that you have this formula, okay, and for radiations to happen, the N0, which is the ratio of the mass of the gauge bosons to the orbital frequency. So for radiation to happen, you need this condition, omega greater than mz prime.
Yeah.
So that basically constant you the mass of the z prime. So if you calculate what is omega, that is of the order of 10 to the minus 19 eV. Now for the super radiance, when you compare with the Schwarzschild radius for typical black hole, you will get the mass scale is of the order of 10 to the minus 11 to 12 eV. So this is a complete different mass scale. So we will not get any bound on those coupling from the super radiance.
Thanks.
Other comments or questions? No? Yes.
So in the last plot, when you showed that G prime, is it the spin independent stuff, or like what is G prime?
So basically, G prime is basically your when you extend your standard model SU3C cross SU12 cross U1Y with another U1 gauge group, okay, you can write a Lagrangian, that is where the standard model say neutrinos is coupled with the Z prime. So you will get psi bar, gamma mu psi and Z mu.
So it's just it's not normalized by anything, it's just the coupling.
Yeah, it's just that coupling, yeah. And then you calculate for that extension what will be the nu bar goes to E plus E minus mediated by Z prime.
Other questions or comments? Okay, if not, let us thank Tanmay.
Thank you.